So this is our first paper, MAT-601, that is real analysis. So this is sixth semester, first paper of mathematics, that is real analysis. Actually, it is real analysis 2, real analysis 2. First real analysis paper already we have seen, that is 501. So before starting, we will just revise the syllabus of this paper. So already I have shared the syllabus in WhatsApp and Google Classroom. This syllabus is also available on university website, so you can download it. So there are total 5 chapters in this syllabus. First chapter, that is limits in matrix spaces. Actually this is second part of real analysis which we have seen in previous semester. Same book is there, that is methods of real analysis by R.R. Goldberg, and chapter number 4 from this book, that is chapter number 1, limits in matrix spaces. In that we will see matrix spaces, limits in matrix spaces. Second chapter, that is continuous functions on matrix spaces. So in that we will see functions continuous on matrix spaces, open sets, closed sets. Third chapter, that is connectedness, completeness and compactness. So in that, so this is chapter number 3. So in that we will see more about open sets, connected sets, bounded sets, totally bounded sets, complete matrix spaces, compact matrix spaces, continuous functions on compact matrix spaces, and last, that is uniform continuity. So this is chapter number 3. Chapter number 4, that is calculus. So in that we'll see sets of measure 0, definition of Riemann integral, existence of Riemann integral, fundamental theorem of calculus, and last chapter, that is Fourier series. So in this chapter we'll just see in definition of Fourier series and some examples on it. So just introduction is there for Fourier series. So this is syllabus of MAT 601, that is real analysis 2. So recommended textbook for this course is Methods of Real Analysis by R.R. Goldberg. And what is scope of this syllabus in this book? So you can see, so in this book, chapter number 4, chapter number 5, chapter number 6, and chapter number 7 for our syllabus. And there is another book. So this last topic, that is Fourier series. It is from second book, that is First Course in Mathematical Analysis by D. Somsundaran and V. Chaudhary. It is of Narosa Publishing House. Or you can just refer same book. So alternately, you can refer same book, that is Methods of Real Analysis by R.R. Goldberg. Same book, and you can refer chapter number 12, and that is 12.1. Same topics are there. So you can refer second book, or directly you can refer single book, that is Methods of Real Analysis by R.R. Goldberg. And what is additional chapter there? So the chapter 12 will be there, and which contains Fourier series. So this is syllabus of this course. So directly we'll start first chapter, that is limits in matrix spaces. So in that we'll see. So this first chapter. So in that we'll see matrix spaces and limits in matrix spaces. So 2 points are there for in our syllabus. So what is textbook content? So you can refer chapter number 4 of Methods in Real Analysis by R.R. Goldberg, and in that, so you'll refer 4.2. In 4.2, yes, articles A, B, and C will be there, and in 4.3, articles only A, C, and D will be there. So 1.1, that is matrix spaces. See, So definition of metric space. Actually, first we'll see definition of metric. See, what is the definition of metric? Metric is a function. So let capital M be any set. A metric for capital M is a function. So you can denote it by row. So row with the domain M cross M and its range contains in the set of positive real numbers, that is close interval 0 infinity, says that. So what is metric? So metric is a function from M cross M to close interval 0 infinity, that is set of positive integers. So rho is a function from M cross M to close interval 0 infinity, and this function satisfies following four conditions. If this function rho satisfies these four conditions, then this row is called metric for this non-empty set M. So capital M be any set. It may be set of integers, it may be set of rational numbers or whatever it is. So row is mapping from M cross M to close interval 0 infinity. So when we say row is a metric, so first condition, row of xx should be equal to 0 for all x belongs to M. Row of xy should be always positive, that is row of xy is greater than 0 if x is not equal to y and y belongs to M. Means if we combine these conditions, it means that so row of xy is equal to 0 if x equal to y and which is strictly greater than 0, means you can write strictly greater than 0 if x not equal to 1. So you can call this as distance. So distance between any two points is either 0 or strictly greater than 0. If these two points are equal or same, then this distance will be 0, and if these points are different, then the distance will be positive. So row of xy is strictly greater than 0 if x not equal to 1. Third condition, row of xy and row of yx both are same. It is true for all xy belongs to M. And fourth condition, that is triangle inequality. So row of xy less than equal to row of xz plus row of zy. Means if we add any point z between x and y, then resulting distance will be greater. So suppose x is here and suppose y is here. If we add any point between x and y, suppose z is there, then what is row of xy? So row of xy will be always less than equal to so row of xz plus row of zy. That is row of xz plus row of zy. So this inequality is called triangle inequality. So if this row, which is mapping from M cross M to close interval 0 infinity, if it satisfies these four conditions, then this row is called metric on M. So what is first condition? Row of xx should be 0 for all x belongs to M. Row of xy should be strictly greater than 0 if x is not equal to y. Third, row of xy and row of yx should be same for all xy belongs to M. And fourth condition, that is row of xy should be less than equal to row of xz plus row of zy. It should be true for all x, y, z belongs to M. So alternately, this condition 4 is called triangle inequality. So what is the definition of metric? So metric is a mapping from M cross M to close interval 0 infinity. It satisfies these four conditions. Then that resulting mapping is called metric on that non-empty set M. So let M be any set. A metric for M is a function row with a domain M cross M and a range containing close interval 0 infinity says that which satisfy these four conditions. So you can observe something about this definition of metric. So, so write it as note, first note. If rho is a metric for yum, then the order for yum row is called metric space. So what is metric space? Metric and metric space, these are two different things. So what is a metric? Metric is a mapping, it is function. And what is metric space? Metric space, it is collection of, see, it is order of here. That non-empty set yum with that metric row, combined it forms metric space. So yum row is a metric space, row is a metric. So yum row is called metric space. If row is a metric on yum, then combinedly yum row is called metric space. So in many cases, we refer metric space yum row simply by yum. So we'll not write yum row, we'll just write yum. So instead of yum row, we'll write yum. So ultimately, it means that. So metric is already defined on that non-empty set yum. So in next section, we'll see some examples of metric spaces. So this is 1.1, that is metric spaces. So in that, so just to have seen definition of metric and what is metric space. So non-empty set with metric defined on that set combined forms metric space. So this is metric space. So what is first example? See, so let's suppose capital R with the set of real numbers and the function rho defined by rho of xy equal to mod of x minus 1. Actually, this is your usual, see, distance. So how you find distance between any two points? Suppose these points are x and y. So what is distance between x and y? So you can find this distance by mod of x minus y. So we observe that rho forms metric for R of real numbers. So we denote the resulting metric space, that is set of real numbers with this metric, that is mod x minus y. So combinedly, we'll denote this metric space by R1. So we call this metric rho the absolute value metric, and this metric space absolute metric space. So you can check, see, so you can check at home this metric rho which we define by rho of xy equal to mod x minus y satisfy all four conditions of metric. So what is rho here? See, what is rho? So rho is a mapping from R cross R to set of positive real number, that is closed interval 0 infinity. And how this rho is defined? So rho is defined by rho of xy equal to mod of x minus y. What is first condition? Question is that check rho forms metric for set of real numbers, that is R. So you can do it at home, very simple. So just a minute. Yeah, it's okay. Yeah, what is first condition? Just a minute. My marker is locked. Yeah. What is first condition? Just a minute. So what is first example? So we consider capital M as set of real numbers, and what is metric? So actually we have to check it whether it forms metric or not. So it is defined by rho of x y equal to mod x minus 1. So you can check first condition. See, it's going to, yeah, what is problem? So first condition, that is rho of xx should be equal to 0. So what is rho of xx? That is mod of x minus x, that will be 0 obviously. So this condition satisfies. What is second condition? Rho of xy, that is equal to mod of x minus y. If x is not equal to y, so this quantity will be strictly than 0. So if x is not equal to y, so obviously mod of x minus y will be positive. Third, rho of xy, that is equal to mod of x minus y, and we can write it as mod of y minus x. So this is property of mod, and which is same as rho of yx. So it satisfies third condition. What is fourth condition? So obviously that is rho of xy is less than equal to rho of, so we'll write it as, sorry, so what is rho of xy? It is mod of x minus y, and mod of x minus y, that is equal to, so write mod of x minus z plus z minus y. So you can add plus minus z, and you can write which is same as mod of x minus z plus mod of y minus z or z minus y, and which is same as, so you can write here which is same as mod of x minus y, which is less than equal to mod of x minus z plus mod of z minus y, and which is same as rho of xy less than equal to rho of xz plus rho of zy. So this rho which we define, by rho of xy equal to mod x minus y satisfy all four conditions of metric, that is first, second, third, and fourth, and therefore it forms metric for set of real numbers. So combining this metric, actually this metric is called absolute value metric. So we call this metric rho, which we define by mod. It is called absolute value metric, and combinedly this absolute value metric set of real numbers forms metric space, and we denote it by R1. So what is R1? So R1, it is a metric space with absolute value metric. Actually, this metric also called distance matrix. So already, so we are familiar. So second example, let us see. So what is second example? So let us take m equal to set of real numbers, usual set of real numbers, and define d, which is mapping from r cross r to set of real positive real numbers, that is closed interval 0 infinity, and how it is defined. So d of xy equal to 0 if x equal to y, and it is equal to 1 if x not equal to 1. Means, so d of xy is either 0 or 1. When it is 0, if x and y both are same, then d of xy will be 0, and if x is not equal to y, then directly d of xy will be 1. So there are only two values for d of xy. So it is either 0 or 1. If x equal to y, then it is 0. If x not equal to 1, x not equal to y, then it is 1. That is distance between x and y. So that is dxy. Any two points for xy belongs to R is 1. If two points are distinct points, then their distance is always 1. So again, you can check whether it forms metric or not. So it forms metric on set of real numbers. You can check all four conditions. So verified D forms metric for R. So you can do, yes. So you can check this D forms metric for set of real numbers. So the metric D, so which satisfy a definition of metric on set of real numbers, surely it satisfy. So this metric D is called discrete metric, and henceforth the metric space RD, that is set of real numbers with this metric D, that is RD, is called discrete metric space. So what is RD? See, RD, what is RD? Actually, RD is a metric space with metric D. So this metric space is called discrete metric space. So first, there is R1. So just we have seen two examples. First, there is R1, and second, there is RD. What is R1? So it is a matrix space set of real numbers. It is a matrix space with respect to absolute value metric, and RD again it is a matrix space with respect to discrete metric D. So these are two well-known matrix spaces on set of real numbers. So in future we'll use these two matrix spaces frequently. So note the examples 1 and 2 show that a given set may have more than one metric. Yeah. So what is R1? Set is different, but metric set is same, but metric is different. So here R row, and here it is RD. So set is same but matrix is different. So we can define different matrix on same set. So this is our observation. Third example, yeah. So fix n, which is integer. So let us fix any positive, yeah, n integer. So if x equal to x1, x2 up to xn and y equal to y1, y2 up to yn, means these are n tuples. X is one n tuple and y is another n tuple, are two order n tuples of real numbers. Means x1, x2 up to xn and y1, y2 up to yn, all these are real numbers. So x and y, these are n tuples. So define row of x1. So here we are taking set as RSTN. What is RSTN? It is set of all order n tuples. You can take x1, x2 up to xn, where all these xi's are real numbers. So this is RSTN. So here we take capital M as RSTN, that is set of all order n tuples of real numbers. So let us define, and I'm taking x and y are two members from this RSTN. So let us define row of xy. So how we define row of xy? It is summation k varies from 1 to n of xk minus yk square raised to half. So you can write this term wise. What is first term? It will be same x1 minus y1 its square plus x2 minus y2 its square plus up to plus it will be xn minus yn its square and raised to half, whole raised to half. So this is value of this summation. So what is row of x1? So it looks like usual distance formula in RSTN. So question is that show that this row forms metric for RSTN. So we'll check all four conditions of metric. So what is first condition? If x equal to y, then what happens? Means if x equal to y, then you have to prove that row of x y equal to 0. So that is our claim here. If x and y are two equal points, then distance between these two points should be 0. So surely if x and y are same, implies that x and y will be same. What is x? See. So x is equal to x1 order n tuple x1, x2 up to xn, and y, that is order n tuple y1, y2 up to yn. If x is equal to y, means this order n tuples are equal, so corresponding components will be same, that is x1 will be same as y1. So what it implies? So if these two are same, it implies x1 equal to y1, x2 is equal to y2. Similarly, x3 will be same as y3 up to xn will be same as yn. It means that x will be same as yk for all k varies from 0 to n. And what we will get? So therefore, what is this summation? So therefore, what is row of? Actually, it is nothing but row of x1. It's square we are considering here. So that will imply, see, summation xk minus yk square. So what will be this quantity? So this quantity will be, so you can check, it will be equal to, what is first term? It will be x1 minus y1 its square plus x2 minus y2 its square plus up to plus xn minus yn its square. But x1 is equal to y1, x2 is equal to y2, similarly xn equal to yn. So that will imply, so 0 square plus 0 square plus up to plus 0 square, and this quantity will be 0. So surely, so this summation will be 0. That is row of xy will be 0. It means that if x equal to y, then row of xy will be 0. Also, you can check if row of xy equal to 0, it implies that x equal to y. So simply you can, yeah, go in reverse direction. So if xk equal to yk, directly it will imply x equal to 1. It means that if row of xy equal to 0, means this summation will be 0. If this summation is 0, that will directly imply xk equal to yk, and that will imply x equal to 1. It means that row of xy equal to 0 if and only if x equal to 1. So what is conclusion of this? That is, see, if row of, or you can write, that is row of xy equal to 0 if and only if x equal to 1. So ultimately it gives first condition. What is second condition? If x is not equal to y, what should be our claim? Our claim should be that row of xy is strictly greater than 0. Means distance between x and y should be strictly greater than 0. But if x is not equal to y, what it implies? It will imply, see, surely it will imply xk is not equal to yk, or for some k, not necessarily all k, but for some k. It means that at least x1 is not equal to y1, or x2 is not equal to y2, or up to xn is not equal to yn, or all these are different, or at least one should be different. So surely it will imply. So what is value of this summation? At least one xk is not equal to yk, or maybe all, but surely at least one should be different, and therefore x is not equal to y. So surely x not equal to y implies that this summation is positive. That is, so square root of the summation, that is row of xy, should be strictly greater than 0. It means that xk minus yk will be strictly greater than 0 for some k, you can write. And surely xk minus yk square should be strictly greater than 0 for some k, and that will imply this summation should be strictly greater than 0, and therefore square root of this summation should be strictly greater than 0. It means that it is, if x is not equal to y, then row of xy should be strictly greater than 0. That is second condition. What is third condition? So row of xy should be same as row of yx. So what is our claim in third condition? Our claim is that row of xy should be same as row of yx. So let us consider row of xy, that is summation xk minus yk square raised to half. But yeah, it's square. So xk minus yk square. So all we know, a minus b square is equal to b minus a square. So you can replace xk minus yk square by yk minus xk square, and which is nothing but row of yx. So that is, what is conclusion of this? Row of xy is always same as row of yx for all xy belongs to RSTN. That is set of all order n tuples. And what is third condition? That is triangle inequality. So let's take any 3 points from RS to n. So x equal to x1, x top to xn, y equal to y1, y top to yn, and I'm taking z, that is z1, z top to zn. These are any three order n tuples. Means these are any three elements of RS to n. So what is our claim? Our claim is that row of xy less than equal to row of xz plus row of zy. That is triangle inequality. See, so for k varies from 1 to n. So let ak is equal to xk minus zk and bk is equal to zk minus yk. So what is ak? So ultimately, what is a1? A1 will be x1 minus z1. What is a2? It will be x2 minus z2, and likewise. What is an? It will be xn minus zn, and similarly, what is b1? It will be z1 minus y1, b2 that is z2 minus y2, up to 2 that is bn will be equal to zn minus yn. So let us make this assumption, and because of that you will write rho of xz. What is rho of xz? By definition of rho, it will be summation xk minus zk square whole its power half. But xk minus zk, we are taking it as ak, and therefore it will be summation ak square. See, and what is rho of zy? Rho of zy will be same as, actually you can write it as, see, so we can write here, which is same as summation mod of, sorry, summation zk minus yk its square, k varies from 1 to n, and whole its power half. But zk minus yk is the same as bk, and therefore write rho of zy is equal to summation bk square, k varies from 1 to n, and whole its power half. And what is rho of xy? So similarly, we'll write it as, it will be summation xk minus yk its square, k varies from 1 to n, whole its power half, and you'll write it as, let's see, summation, it is xk minus zk, see, plus, see, you'll write it as xk minus zk plus zk minus yk whole its power 2 and its power half. So xk minus zk is ak, and zk minus yk it is bk, and therefore you'll write rho of xy as summation ak plus bk its square and whole its power half. See, so therefore it will be like this. So Deuce, what we should prove here, if we replace x and y by ak and bk, so what is our ultimate claim? It will be that, see, summation ak plus bk its square and whole its power half should be less than or equal to summation ak square whole its power half plus summation bk square whole its power half. And actually this is nothing but Minkowski inequality, which is, yes, not part of our syllabus. What is Minkowski inequality? Minkowski inequality is that if S equal to Sn, sequence Sn, n varies from 1 to infinity, and T, it is another sequence Tn, n varies from 1 to infinity, are two square summable sequences. So what is L square? L square is space of square summable sequences. Space of square summable sequences, that is L square. What is L square? L square, it is set of all sequences. Sequence S, it is set of all sequences S, that is Sn, n varies from 1 to infinity, says that summation of Sn square n varies from 1 to infinity is finite. It means that if we square each term of the sequence Sn and if we add all these terms, then that summation should be finite. So such type of sequences or set of such type of sequences is called L square. Actually, it is space. Actually, it forms metric space, and therefore it is called space of square summable sequences. So S and T are two square summable sequences. Then what is S plus T? So it will be Sn plus Tn. Then it is again L square summable sequence. And what is Minkowski inequality? See, actually, this is less than equal to this. This inequality. Then summation Sn plus Tn square raised to half is less than equal to summation Sn square its power half plus summation Tn square its power half. So this quantity is less than equal to addition of these two summations. So using Minkowski inequality, so rho satisfy the requirement of, so directly we get it from Minkowski inequality. So there is no need to prove this inequality. Actually, this is not in our syllabus. So therefore we skip this. So directly you can write using Minkowski inequality. So we get triangle inequality. And this is our fourth condition. And therefore rho satisfy the requirement of metric and therefore it forms metric space. So we denote R as to n the metric space formed by the set of all n tuples of real numbers with this metric rho. The metric space R as to n is called Euclidean n space. What is Euclidean n space? R as to n. So we call it as Euclidean n space. A set of all order n tuples. It forms metric space under metric rho, which we define. So what is rho? See, we define rho by rho of xy equal to summation xk minus yk square and whole its power half. So under this metric, this RSTM forms metric space and we call this metric space as Euclidean n space. So in future, we'll use this example. So we'll stop here.